Welcome to Runtime Atlas. Today, we will take a quick look at etcd in Kubernetes. If the API server is the front door of Kubernetes, etcd is the memory behind that door. It is where Kubernetes persists the state it needs to remember, so the whole cluster can keep moving toward the desired state. First, remove a common confusion. etcd is not where your application data lives. It does not store container images, pod logs, or the rows inside your app database. It stores Kubernetes control plane data, objects, configuration, and state. In Kubernetes, nearly everything important is represented as an API object. A pod, a service, a config map, a secret, or a node record can be created, read, updated, and watched through the Kubernetes API. The serialized state of those objects is persisted in etcd. Most clients do not talk to etcd directly, they talk to the Kubernetes API server. The API server authenticates the request, authorizes it, validates the object, runs admission checks, and then writes the accepted state to etcd. Imagine you create a pod. Kubectl sends the request to the API server. If the request is valid, the API server records the pod object in etcd. From that moment, the cluster has a durable record saying this pod should exist. This is why desired state matters. When you ask for 3 replicas, that intent becomes stored state. Controllers keep comparing the stored desired state with what is actually running. Then they take small actions to close the gap. Kubernetes components react by watching the API server. The scheduler watches for pods without a node. Controllers watch their objects. The API server gives them a consistent view backed by etcd, so components can respond when the stored state changes. A cluster is full of concurrent changes. 2 controllers may read related objects. A user may update a manifest. A node may report status. etcd gives Kubernetes a consistent ordered history of persisted changes, and Kubernetes exposes versions so clients can reason about what changed. etcd is critical, but it is not the scheduler and it is not a controller. It does not decide where pods run. It stores the facts. Other control plane components read those facts through the API server and decide what should happen next. For reliability, etcd usually runs as a small cluster, not just one process. Kubernetes documentation recommends an odd number of members. etcd is leader based, so followers need timely heartbeats from the leader to keep the cluster stable. The key idea is quorum. etcd prefers correctness over guessing. If the cluster cannot maintain leader stability, Kubernetes may keep existing workloads running, but new state changes can stop. That is why etcd health is control plane health. etcd is sensitive to disk and network performance. Slow disk, network latency, or resource starvation can delay heartbeats and writes. When etcd becomes unstable, the control plane may struggle to record changes, even if worker nodes are still running current containers. Because etcd contains cluster state, backups matter. A snapshot can help recover after a serious control plane failure. But the snapshot can contain sensitive Kubernetes data, so it must be protected, encrypted where appropriate, and tested before you need it. Kubernetes secrets are also API objects. That means their persisted data is part of the cluster state path. In real environments, you should understand encryption at rest, access control, backup security, and who is allowed to reach the control plane storage layer. When cluster changes stop working, follow the path. Can you reach the API server? Is etcd healthy? Is there a leader? Are disk and network delays causing instability? This mental path is more useful than memorizing isolated commands. Here is the mental model. The API server is the only front door. etcd is the durable source of truth. Controllers and schedulers react to stored state. Protect etcd, back it up, and remember, if Kubernetes cannot safely write state, the control plane cannot safely move forward.